we have seen so far what is a pipeline, how a pipeline works. Now, in this lecture we shall be talking about pipeline scheduling, which means how we can feed the inputs to a pipeline such that no conflict or so called collision occurs in any one of these stages. Now, for a linear pipeline where the stages are connected as a linear chain, this problem does not arises because we can potentially apply one new set of inputs every clock cycle. But if there are feed forward and feedback connections in a pipeline in general for a nonlinear case, then the calculation of the schedule is not so easy or trivial. So, here we shall be basically talking about that pipeline scheduling. So, we take the same example of a nonlinear pipeline we saw earlier. So, this is a simple enough example which you can illustrate. There are 3 stages S1, S2, S3. Well, here we are not showing the interstage latches which are also there, but this is only for illustration. This arrow shows how the data flows from one stage to the other. And here we are assuming that not only the pipeline is nonlinear in the sense that there can be data flow say from S3 to S1, S1 to S3 and so on, but it is a multifunction pipeline, which means we have the same pipeline which can either compute a function x or compute a function y. Well, you see, you can take an analogy for an arithmetic pipeline where you can have a general pipeline where both multiplication and addition can be carried out. But of course, all of these stages will not be used for the 2 cases. We can selectively use some cases. So, the stages, maybe some of the stages will be using for more than one clock cycles and so on. Okay? Fine. So, the operation x, which is represented by this reservation table, this requires 8 cycles to complete, and this is the sequence of stage occupancy. First the input data goes to S1, then to S2, then to S3, then again to S2. So, you see S3 to S2 there is a connection, from S2 again to S3, S3 to S1, you see S3 to S1 also there is a connection, then S1 to S3 a skip, there is a feed forward connection like this, and finally S3 again to S1, then it finishes. So, from S1 it finishes and it goes out. Similarly, for the function y, it again starts with S1, it goes to S3, S2, S3, S1 and finally S3 where it finishes. So, from S3 it exits. So, x will exit from here, y will exit from here. Okay. So, with the help of this example, let us explain how scheduling of this pipeline can take place. Scheduling actually means, you can say that means if you are not careful enough when you are applying the consecutive inputs, say the first input which during computation may be in S2, the second input is also trying to go into S2 at the same time. So, it cannot happen that way, So, the one of them has to wait. Fine. So, we shall be doing something called latency analysis. Latency is actually the delay between 2 successive data inputs or initiations it is called, that are fed to the pipeline. So, our objective is to calculate the latency value or the sequence of latency values which will not result in a collision in any of the stages, right. Okay. So, latency, as I said, it is basically defined as the number of time units or clock cycles between 2 successive initiations, right. 2 inputs applied to the pipeline, what is the minimum number of time steps we need to give between them. And as I said, if we are not careful enough, then 2 or more initiations may be trying to use the same stage at the same time, which results in a collision. Some of the latencies will definitely result in a collision, and such latencies are referred to as forbidden latencies, we cannot use those latencies. So, how we can estimate the forbidden latencies? We can simply calculate the distance between two check marks in the rows of the reservation table. Let us take an example. Let us see the first example, the reservation table for x. So, you see here there are so many check marks. There are check marks at a gap of 2, there are check marks at a gap of 4, this and this, there are check marks at a gap of 5, and this one gap of 7. So, these are all forbidden latencies, distance between any two pairs of check marks. So, for this reservation table, the forbidden latencies are 2, 4, 5 and 7. Similarly, for the other functionality, this y function, here you can see 2 and 4, here also it is 4. So, here the forbidden latencies are only 2 and 4, right. So, this is the first step in our analysis to list or enumerate the forbidden latencies. Now, a latency sequence is defined as a sequence of permissible non-forbidden latencies which do not result in a collision. See, latency sequence is like this. Latency, as I said, it is the gap between two successive data I am applying. So, I can say that I am using a latency sequence of 1, 2, 1, which means between the first and second inputs I give a gap of 1. Between second and third input I give a gap of 2, between third and fourth input I again give a gap of 1. So, I say that I am using a latency sequence of 1, 2 and 1. Okay. This means this sequence can be any arbitrary delay gaps that you can specify, and if this sequence repeats in time, then we call it a latency cycle. Latency cycle is nothing but a latency sequence where the same subsequence is repeated. Like let us take an example. Suppose we use a latency sequence like this 1 3 1 3 1 3 and this repeats indefinitely, right. So, we can say or we can write in a compact notation that it is a latency cycle 1 3. This 1 3 will be repeating indefinitely, right. Similarly, if I have a case where the same latency 2 2 2 2 2 is to be used, then I can write it as a latency cycle containing a single latency 2, right. Okay. So, talking about the two functions, the first function we have already seen that the forbidden latencies are 2, 4, 5 and 7. Well, here we are just listing some of the forbidden latency cycles or the some of the latency cycles which you can use, the possible ones, but how to get this we shall be showing shortly. Let us say here one of the possible latency cycles which do not result in collisions is 1 and 8. So, 1 8 1 8 like that you proceed. This will result in an average latency of 4.5 because 1 plus 8 is 9 divided by 2. If it is a 3 3 3 like this 3, here average latency is 3 because 3 is a non forbidden latency and multiples of 3s are also not there, 6 9 these are not there. Similarly, 6 is also a feasible latency cycle 6 6 6 average of 6. So, in this case the minimum latency is resulting for the second case. Similarly, for the function y where the forbidden latencies are 2 and 5, we have several alternatives. Well, we can use 1 5 1 5 this kind of a cycle because 1 is not forbidden, 5 is also not forbidden. This results in an average of 3. We can use 3 3 3, this also results in an average of 3. Also we can use 3 5 3 5 alternating, for this average will be 4. Now, the cycles where there is no change, the same latency have to be used, these are referred to as constant cycles, like here 3 6 and here 3, these are examples of constant cycles. Now, our objective is to do something called collision free scheduling. How to schedule the pipeline, how to determine the latencies dynamically See, dynamically means when the data comes, means we should be able to automatically find out whether we can feed the next data or not. That is called scheduling. We shall be looking into this. Scheduling such that there is no collision. Well, of course, the main objective is to obtain the shortest average latency. Well, we start by defining a data structure or a vector you can called collision vector. It is a bit vector. Collision vector is defined as follows: if there are n number of columns in the collision in the reservation table, then you see it is like this. If we have a reservation table, there are rows, there are many columns. Let us say there are n number of columns, right. So, in the worst case there can be a check mark here and check mark here, which will result in a forbidden latency of n minus 1, gap of n minus 1. This can be the maximum forbidden latency, right. So, here we have mentioned the same thing. The maximum forbidden latency m cannot be greater than n minus 1, it can be maximum n minus 1, and the permissible latencies that we shall be using for scheduling, this obviously has to be less than or equal to m minus 1, because more than m does not make sense, because effectively if there are 5 stages in the pipeline and I am saying that I have to give a gap of 6, then there is no use in having the pipeline. Anyway, I will be waiting for 6 time cycles to feed the next data. So, that is not a good way of scheduling. So, we will say that the permissible latencies p will be satisfying this inequality. Maximum forbidden latency is m minus 1 and minimum is of course 1. Now, we define the collision vector as an m bit vector, where m is this maximum forbidden latency, right. C1, C2 to Cm, where a particular bit is 1 if latency I causes a collision, and that bit is 0 if the latency I does not cause a collision. And because m is the maximum forbidden latency, by definition Cm is always 1, because m is the maximum forbidden latency. So, this bit has to be 1, right. So, for the two functions you see Cx, the forbidden latencies were 2, 4, 5 and 7. You just count 1, 2, 3, 4, 5, 6 and 7, 2, 4, 5 and 7, and function y from the right side again 2 and 4. These are the forbidden latencies. So, the collision vector for the two cases are defined like this. Now, from the collision vector we construct a state diagram, where we define the states as the status of collisions at a particular point in time. That means, which time gaps or latencies can result in a collision at that point in time. That is one state, and the state transition diagram can contain multiple states. You can go from one state to the other, right. And the initial state is the collision vector, and from the collision vector, from any state you can move to some other state by advancing the time by some number p. Suppose you are currently in time t this state. So, if you advance the time by p, what you do? So, whatever is the present state, you shift it right by p positions. See, what is the meaning? Suppose I am in a present state where my bits are something like this. So, which means that from time 1, 2, 3, 4, 5, 6, 7, 8 and 9, 3, 7 and 9, these are my forbidden times where I cannot feed the next input. These are forbidden latencies. But now say if I advance my time by 2 steps, then whatever was 3 now, after 2 steps this will become 1, 7 will become 5, 9 will become 7. So, actually we are shifting this right by 2 positions. So, this 1 will come here this 0 0 0 1 0 1 and 2 zeros will be shifted in. This will be my new status after time 2. Now, the collisions will occur at time 1, 2, 3, 4, 5 and 7, right. This is the idea. So, the next state is obtained by shifting it right, and of course, the initial collision vector which was there, that lists the forbidden latencies. So, the latencies which are forbidden will always remain forbidden. So, whatever you have obtained by right shifting, you will have to do a bit by bit logical OR with the initial collision vector also. So, that wherever there is a 1 in the initial collision vector, it will remain a 1 in all the states, because those will always be forbidden. You cannot use that latency at any point in time. Okay. So, let us take an example, that same example. This is the state diagram for function x. Let us see how we have obtained this. So, we have said that for this function the collision vector was this, it indicates the forbidden latencies of 2, 4, 5 and 7. So, this will be my initial state. Now, from my initial state I can advance my time only by that amount where I have zeros which are not forbidden, which means time 1, 3 or 6 or 8 or more. If I advance it by 1, you see my collision vector was 1 0 1 1 0 1 0, 1 0 1 1 0 1 0. Now, if I advance it by time 1, so I will be doing a right shift 1 0 1 1 0 1 and a 0 will come in, then you do a bit by bit OR 1 1 1 1, all will be 1, right. Similarly, suppose I use 1 2 3, I use p equal to 3, then I shift it by 3 positions 2 3. So, it will be 1 0 1 1 and there will be 3 zeros coming in. So, again do a bit by bit OR 1 1 0 1 1 0 1, this will be my new state, right. In this way you can calculate, okay, for all. So, from this initial state which represents the collision vector, if I go or advance time by 1, I go to this state just like I calculated. If I advance it by 3, I go to this state. If I advance by 6, this you can check, you will also arrive at the same vector. But if I advance it by 8, that means if you shift it by 8, everything will become 0. 0 or with the initial vector will be the initial vector itself. Similarly, from here there are no zeros, so you can only have 8 or more. Shift it by 8 positions, all will be zeros, or with this you get back this. So, this will be an arrow back. And from here you see 1 0 1 1 0 1 1, 1 0 1 1 0 1 1. So, here you have 3 and 6. So, if you shift by 3, 1 2 3, it will be 1 0 1 1 and 3 zeros 1 1 0 1 1 0 1. So, you are in the same state. Similarly, if you shift it by 6 positions 1 2 3 4 5 6. So, this 1 will come here and all rest are zeros. So, if you do OR, again it will remain the same state, right. So, you see from here 3 and 6 are resulting in a self loop that you remain in the same state. Okay. Similarly, for the other function where the collision vector is 1 0 1 0, 2 and 4 are the forbidden latencies. So, from here you can advance time either by 1, shift right one position or all will be ones, or shift right by 3 positions and or last bit will become 1. And once you are here 1 2 3, 3 is only the permissible, shift it by 3 or it same state will remain. Of course, 5 plus will bring it back to the origin, here also 8 plus will bring it back. Here also there are no zeros, so only 5 plus it will bring it back. So, from here you will have to look at cycles. See, for example, in this diagram the cycles are 3 is a cycle, 6 is a cycle, 1 8 is a cycle, simple 8 is a cycle, and here 3 is a cycle, 1 5 is a cycle, only 5 is a cycle, and there are other cycles 3 5, 3 8, 6 8 are also cycles. So, from the state diagram we can determine the latency cycles such that the minimum average latency is minimized. So, when we talk about a simple cycle, a state appears only once. This is of course the kind of cycle that we want, because we do not want a cycle like this where I am telling 3 3 8 3 3 8, 3 is appearing twice, that I shall not be considering as a feasible cycle. Okay? I shall only be considering simple cycles, and greedy cycles are those where from every state we shall only be taking the outgoing edges with minimum label. Like in the previous example, if I am here, the outgoing minimum is 1. So, I will have to go 1, here there is only 1, this is one greedy cycle, and if I am here 3 is my minimum outgoing edge. So, this is my only greedy cycle. From here again 1 and 5 is greedy cycle, from this state 3 is a greedy cycle. So, these are the simple cycles for function x, all possible simple cycles where the numbers are not repeated. Out of them there are 2 greedy cycles. Similarly, for the function y there are 4 simple cycles and 2 greedy cycles. And for both the cases, if you only look at the greedy cycles, the minimum average latency or MAL is 3 in both cases. In both the cases it is 3 and 1 5 average is also 3. Okay. Now, the scheduling algorithm looks or goes as follows. Suppose I want to build a control circuit which will automatically tell me that whether it is safe to feed the next data or not. So, load collision vector in a shift register. So, this is my original collision vector, and well, shift register is initialized to 0. I initially load it 0 or of this. So, I load my collision vector in the shift register initially. So, load CV in the shift register. Now, at every point in time I do a right shift where I feed a 0 and I check whether a 0 is coming out or a 1 is coming out. So, if a 1 is coming out, which means that next time instant is forbidden, you cannot feed a data at that time. So, if the LSB is 1, last bit that is coming out is 1, then do not initiate an operation, simply shift the register by 1 bit with 0 insertion, and in the next iteration, next clock cycle, again check it whether in the next clock you are allowed to feed or not, right. But if you find that it is a 0, what does that mean with respect to the state diagram? That here 0 means you are going to the next state. Next state means you have to shift right and OR with the collision vector, right, to get the new state. So, the same thing we are doing here. Here you see, so we initiate an operation, if the bit is 0, initiate an operation, then we shift it right and then we OR it with the collision vector. Whatever is the shifted value, we OR it with the collision vector and load it back into the shift register, and this process we repeat. So, if you just think, so whatever we are doing here is exactly the process by which we were computing the state diagram. So, at every step we are trying to shift it by a position, by a number of bits which is allowed, that means 0. So, we go on shifting till the next 0 comes, then we OR it with the collision vector, that will be my new step. And we always move when we get the first 0, that means we are looking only for greedy cycles. From every state we are moving out following the smallest or the least value of the cycle, right. Fine. Now, there are ways to optimize a pipeline schedule. Now, I am showing you one method with the help of an example. Suppose we have a nonlinear pipeline like this, where the reservation table is as follows, where you see in some of the time steps like 4, 2 of the stages are simultaneously used, and here the forbidden latencies are 1, 2 and 4. So, 1 0 1 1. So, the state diagram will be very simple, you can either shift it by 3 or 5 or more. Obviously, 3 is a minimum average latency. Now, what we are exploring here is that okay, can we insert some delay elements in the pipeline, some dummy stages which do not compute anything, just eat up some clock cycles. So, you may say that well, if you insert dummy stages which do nothing, simply eat up some cycles, then my time will be increasing. Well, your time may be increasing for a single computation, but when you are feeding many data one after the other, earlier there were a lot of collisions, but if you insert those delays, maybe the number of collisions will become less. Okay? That is the idea. So, for this example, suppose I insert delays like this. This was my original pipeline. I insert delays in 2 of the branches, one delay here, one delay here. That means, while going from S3 to S1, I put a delay, and S3 to S1, S3 to S3 and S3 to S1 also I put a delay. So, earlier my reservation table was this. Now, in the reservation table there will be 2 additional dummy stages introduced, and because of the delay, some of the check marks will get shifted. This will get shifted here, this check mark will get shifted here, and let us say here after S3 you first go to D1, you are going to D1, then you are going back to S3. Earlier you are directly going to S3. Similarly, for this, from S3 you are going to D2, this was S3, from D2, then you are going to S1. Okay. Now, for this one again it is a slightly more complex. Here the latency, the forbidden ones are 2 and 1, 2, 3, 4, 5, 6. So, 2 and 6. So, if you just compute the state transition diagram in a similar way, you can check this. This is the state transition diagram which is obtained, and if you compute the greedy cycles, in this case this will be the best cycle 1 and 3, 1 3 1 3 1 3, which will be resulting in an average of 2. Earlier it was 3, now by inserting the delays we have achieved an average of 2. So, by inserting this kind of dummy delay stages, the performance of a nonlinear pipeline can be improved. This is something you have to keep in mind. Okay. Now, let us work out a couple of examples. Let me work out one of them, and one of them I leave as an exercise for you. Let us take the smaller one. So, here we have a reservation table where there are 3 stages, S1, S2 and S3, and there are 4 time steps which are required for a computation. This is a very simple example where my only forbidden latency is how much? 1, 2, 3, nothing else. So, my collision vector will be 3, 2, 1. This will be my collision vector. So, if I draw the state transition diagram now, this will be my initial state. Now, I can shift it by either 1 or 2, 1 is possible, 2 is possible. So, if I shift it by 1, what will happen? I will shift it right by 1 position, it will be 0 1 0. I OR it with the original collision vector, I get 1 1 0. So, my new state will be 1 1 0. If I shift it by 2 positions, it will be 0 0 1. Again, if I OR it with the original collision vector, I get 1 0 1. Now, once you are here, the only 0 is here 1. If you shift it by 1 position, it will become 0 1 1, and OR it with original, it will become 1 1 1. So, if you shift it by 1, you land up in another state 1 1 1, and here 2 is the only forbidden. If you shift it by 2 positions, it will be 0 0 1, OR with 1 0 0, it will remain in 1 0 1. So, if you have 2, it will remain here. So, this is complete for the zeros. Now, for the ones, for the other ones, it will be 4 or more. From any state, if it is 4 or more, you go back to the initial state. Here also 4 or more, from here also 4 or more. So, if you analyze this state transition diagram, you will see that your minimum cycle is this 2. So, minimum average latency will be 2, right. So, like this, given any reservation table, you can first calculate your state transition diagram, then from here you have to find the cycle that results in minimum average latency, that will be your minimum, right. Fine. Let us work out another example. This directly do not relate to instruction scheduling, but a problem of pipelining. Let us say what this statement, it says a non-pipeline processor X, what is no pipelining, has a clock frequency of 250 megahertz and a CPI of 4. Because there is no pipelining, it takes 4 clock cycles to execute every instruction. There is an improved version Y, which is having a 5-stage linear pipeline, but because of the latch delays and other overheads, the clock frequency is reducing to 200 megahertz. Now, there are two things it is asked, that if I am running 5000 instructions on both the processors, what will be the speed up? So, how fast will Y be with respect to X? And secondly, what will be the MIPS rating of the two processors? Let us work out for the processor X. Let us calculate the execution time. So, you recall execution time is given by the instruction count multiplied by the cycles per instruction multiplied by the clock cycle time. So, for the first processor, execution time, let us call it x t of x will be, there are 5000 instructions, CPI is 4, it is running at 250 megahertz clock. So, it will be 1 by 250 mega, this many microseconds. So, if you just calculate this, this comes to 80 microseconds. Similarly, the execution time of the pipelined processor, well, again instruction count is 5000. Now, for a pipelining, in the ideal case CPI is 1, because in every cycle you can feed a new instruction and one instruction will be completing every clock cycle. And now, your clock cycle has slowed down, it is 200 megahertz. So, it is 200 mega. So, if you just calculate, this comes to 25 microseconds. So, the first answer, the speed up of course, your Y is faster than X. So, the execution time of X divided by the execution time of Y, 80 by 25, it is about 3.2. Now, second part of the problem concerns the MIPS rating. So, again for the machine X, you see, for executing 5000 instruction you require 80 microseconds. So, you can say that in 80 microseconds you are able to execute 5000 instructions. Therefore, in 1 second how many you can execute? This is your MIPS, million instructions per second, you see 5000 by 80, micro is there. So, micro is 10 to the minus 6, when it goes up it will be 10 to the power 6, it will be mega, million instructions per second. So, this comes to 62.5 million instructions per second. Similarly, for y it is 25. So, 25 microseconds is required to execute 5000 instructions. Therefore, in 1 second you can execute 5000 by 25, again there is micro. So, this many million instructions per second. This gives 200 MIPS and here it was 62.5 MIPS. So, you can see that the MIPS rating for the pipeline processor is significantly higher, which is very typical, right. So, with this we come to the end of this lecture. Now, in this lecture we talked about the various ways in which we can calculate the permissible latencies in a general pipeline. You see, normally if it is just a linear pipeline, all these calculations will not come into the picture, but if it is a more complicated scenario, complicated kind of a pipeline, non-linear properties, feed forward and feedback connections, then this latency calculation and latency analysis becomes important. Thank you.